Okay. All right. Anyway, now it will record. Okay. Yeah. Okay. So let's start with. Oh my God, it's still doing this. Press this. Okay. So let's have x1. So three variables will take x1, x2, x3, and s1, s2. Oh, I didn't keep much space for. All right. Okay. Anyhow. Should do. Okay. So. All right. Anyhow. So let's have the following numbers. Let's take 2x1 plus 3x2 plus x3 less than or equal to 100 and 100. Okay, let's take. Okay, this is B. And let's have x1 minus x2 plus 3x3 less than or equal to 160. Okay. And Cj's here are the coefficients. Suppose this is 2, 3, and minus 1. Okay, 2, 3, minus 1. Okay. All right, so what do we get? Well, we need to put in our identity matrix, slack variables, 0 and 1 here. Okay. And so we can now, okay, I'll just pull this down a little, push this up a little. Okay. Okay, so now what are the basic variables to start with? Well, because of the identity matrix, it will be S1 and S2, right? S1 and S2. Okay? And so currently x1 equals 0, x2 equals 0, x3 equals 0, S1 equals 100, S2 equals 160. Okay? Now to get delta J. Well, in the first step, if you just recall, since we're going to anyway take 0, it will just be the negative of the Cj. So first step is automatic, minus of the Cj's. Yeah? Because we're doing 0 minus that, right? So anyway, it'll always be negative of that. First step. From next step onwards, we'll have to do that, right? So minus 2, minus 3, plus 1, 0, 0. Oh, it's a horrible 0. Okay, 0, 0, and 0. Okay, first step is simple. Okay, so is it optimal? No. Why? Because of negative delta J. So which is the entering variable now? So which one is most negative? Minus 3. So this is the entering variable. And remember, we only take positive values in the pivot column. There's only one positive value. So in this case, this has to be our pivot. If there's only one positive entry in the pivot column, that has to be the pivot, right? Whatever big or small number it is. And so this has to be the exiting variable. So in this case, we don't need to do all that theta because there's only one positive entry. That has to be the pivot. So what will our basic variables now be? Okay. So basic variables now will be, so S1 is replaced by X2. So, oh God. So X2 and S2, just like what happened last time, right? X2 and S2 are the basic variables now. Everyone agrees? Yes? All right. Now, this time the pivot is not equal to 1. So we have to make this 1. So what do? We divide all entries in the pivot column by 3. Okay, so this will become 2 by 3. 3 by 3 is 1. 1 by 3 here. 1 by 3 here. 0 and 100 divided by 3. Now, you'll say that, okay, why not put everything in this decimals? Well, fractions are actually very useful, actually. What will happen is all the same fraction will come everywhere. And when we do the next step, that will go away and some new fractions. So it's better to keep fractions. If some calculators have this type of fraction, so you can use those. Otherwise, otherwise you can practice using fractions a little, but not difficult. Don't worry. Okay, so we did that. Now we want to have a 0 in the x2 column in the S2 row. So I want a 0 to come here. How do I get a 0 to come here? Well, I have to subtract some multiple of the pivot row from the pivot row from this row. So in this case, because there's a 3 here, I have to divide that by 3. I'll get a 1. And then if I add here, I'll get 0. So second row plus 1/3 of the pivot row will give me what I want. Now, of course, would you want me to show you a sort of a shortcut too? I think I'll show you the shortcut because this pivoting using this transformation is difficult. So let me show you the shortcut straight away. This is called cross multiplication. Okay. How we arrived at 0. Okay, yes. Now the whole point is we're going to arrive at the 0 because what we're doing in this simplex method is we're moving the identity matrix to the basic columns. And so in our first table, we had 1, 0, 0, 1 for S1, S2. Now we want an identity matrix here. So X2, S2. So the X2 column will be the first column of the identity matrix. S2 column will be the second column. Okay, so this is how this method is going to work. Now I'm going to get other things by doing some cross multiplication. So let me show you how this works. So I want to find this entry, correct? So what I'll do is I'll start here and multiply into the element I'm changing. So 3 into 1 is how much? 3. And then I might subtract this product here. 3 into 1 minus 1 into 2. So that's 3 minus 2. How much is that? 5. And I divide by the pivot entry. So that becomes 5 by 3. So I start here, multiply into this. 3 into 1 minus 1 into 2. So 3 minus 2 is 5. Divided by 2 is 5 by 3. Shall we try the next one? Right. Let me do that in a different color. So 3 into 3 is 9. Minus 1 into 1 is plus 1. So 9 plus 1 is 10. 10 divided by 3 is 10 by 3. Okay. And last one, last two rather. Okay, maybe different color. Red, okay, orange. So take this, multiply into this. 3 into 1 is, that's done, sorry. This one, 3 into 0 is 0 minus 1 into 1. So 0 plus 1 is 1 by 3. So 1 divided by 3. And last one is the B column, purple, let's take purple. So this into 160, 3 into 160 is 480, minus 1 into 100 is 580. 580 divided by 3 is what we want. 580. Okay, so this becomes our new basic feasible solution. So what is the value of x1 now? x1 equals 0. x2 equals 100 by 3. s1 again equals 0. s2 equals 580 by 3. Okay. Hussein, you wanna? Huh? Oh, okay, fine. Okay, so right. What do we do next? Now that we've got another basic feasible solution, we calculate delta J's. Right? This is a not never-ending process, but ending. Right? How is S2 second value is 0? Second value is 0. No, see, the whole point of this is we're going to get an identity matrix in these two columns. X2 column, which is the first column of the identity matrix, S2 column, which is the second column. That's why we got this 0 here. It's automatic. This method gives us that 0. Okay? All right. As we do it, you'll see. Don't worry. Okay? Okay? All right. Okay. Now, let's get our CB. What is our CB? Well, only X2 has a coefficient, and that coefficient is 3. So let's find out delta J. Okay. So 3 into 2 by 3 is 2. 2 minus 2 is 0. Oh, it's going to be optimal, I think. Okay. 3 into 1 is 3. Minus 3 is 0. 3 into 1 by 3 is 1. Minus 1 is 2. Oh, it's optimal already. Okay. That's a bit sad, actually. Okay. 3 into 1 by 3 is 1. Minus 0 is 1. And 3 into 0 is 0. And 3 into 1 by is that? Is 100. And so, our solution happens to be optimal. Okay. Oh, that's no fun, actually. Okay. We'll do a longer problem now. All right. So, this is optimal. And in our optimal solution, x1 equals 0, x2 equals 100 by 3, s1 equals 0, s2 equals 500 by 3, and z equals 100. Okay? So we'll try a little bigger one now. Okay? Everyone is ready? Don't save. No need to save. This is recorded anyway. Okay. All right. So let's have a slightly bigger one this time. Okay. Okay. It's going to take more steps, so I'll preempt it and have a little bigger. Okay. This time let's write down the things. Otherwise, okay. So x1, x2, x3. And let's have 3 constraints also. S1, S2, S3. Okay? This is nice and confusing. Right? And B here. Okay, and let's draw a line here. This is vertical. Okay. Right? And for the moment, I'm not doing greater than equal to other things. It's more, okay, we'll talk about it. So all of these we're dealing with less than equal to constraints only. We'll talk about what to do with greater than equal to constraints. So S1, S2, S3 are the basic variables. And we'll take a line like this. Okay. And okay, let's have, say, x1 plus 2x2 minus x3 less than or equal to 160. Let's take 2x1 minus x2 plus x3 less than or equal to 140. And say minus x1 plus, okay, without x2 plus 2x3 less than or equal to 180. Okay, so let's have it that way. Okay, let me just redraw the 0 a little. Okay, and suppose all of them are less than or equal to, oh, and the CJs, let's have as, say, 2, 3, and 1. Okay, so this time let's have it like this. And of course, to start with, since all of them are less than or equal to, I'll have my identity matrix here. So 1, 0, 0, 0, 1, 0. Okay, this is another. And 0, 0, 1. Oh, horrible. 0, 0, 1. Okay, so let's write down the delta J quickly. It's just negative of this. So minus 2, minus 3, minus 1, 0, 0, and 0. And of course, Z is also equal to 0. Okay? So this is our initial solution. So what is the entering variable? X2, right? X2 is the entering variable. Yes? And what do we do? Look for positives here. Is there any positive entry here? Only 2. So again, this is our pivot. It has to be a pivot. Nothing else is there. And so this is the exiting variable here. Okay, so what will our basic variables now be? Again, X2, S2, and S3. Oh God. S2 and S3. Okay, so let's draw a line down here. Okay, and again, we have to divide by 2 everywhere. So everything is divided by 2. So first one becomes 1 by 2. 2 by 2 is 1. This is minus 1 by 2. Oh, sorry. 1 second. So could you please? Okay, yeah. All right. Why did we get these delta J's? Well, if I put CB, I can put CB if I want, right? If I put CB, what are the CBs? Well, all S's have the CB as 0. So this would have been 0, 0, 0. And then I'd have to calculate 0 into 1 plus 0 into 2 plus 0 into minus 1 minus 2. But for sure. So in the first step, it will always just be the negative of the objective function. So objective function here is 2, 3, 1. It will just be minus 2, minus 3, minus 1 for the first step. After that, you will have to calculate separately. All right, Rajesh? Okay? All right, anyway, we'll just continue. So we're dividing still. So this becomes 1 by 2, 0, 0, and finally 160 by 2 is 80. Okay? All right, now comes the next step. So remember, where do I put the identity matrix? I put the identity matrix in these columns. So the first column comes here, 1, 0, 0. Second column comes here, 0, 1, 0. And third column comes in S3, 0, 0, 1. Right? So that will automatically come. Yeah, I'm sorry, it's getting a bit squashed towards this side, but anyway, it's identity, so not a problem. The other numbers are more important. Okay, now, how do I do the rest of it? Well, I cross multiply. So for example, first one is 2 into 2 minus 1 into minus 1. So 4 plus 1 becomes 5 by 2. And remember, divide by the pivot. So 5 divided by 2. Next one is 2 into minus 1 minus 1 into 0. How much is that? Minus 2 divided by 2 is minus 1 still. No change there. Okay, next one is 2 into 1 minus 1 into, okay, so be careful. 2 into 1, that's 2, minus 1 into minus 1. So 3 minuses. What happens when you multiply 3 minuses? It's just 1 minus. So 2 minus 1, which is 1 divided by 2. So 1 by 2. Okay. Next one is 2 into 2 minus 1 into 0. So 4 minus 0 is 4 divided by 2 is just a 2. Okay. Now the rest, do I need to still draw arrows or can I just write down the rest? I can write down? Okay, I'll show you, but okay, next one is 2 into 0 minus 1 into 1. So that's plus 1 by 2. And last one is 2 into 0 minus 1 into 0. So just 0. Okay. Last column, 2 into 140 minus 1 into 160. So 280 plus 160. What is 280 plus 160? 420? 420, but divided by 2. 420 divided by 2 is 210. And the last one, 2 into 180, that's 360, minus 0 into 160, so that's still 360, divided by 2 is 180. Notice one interesting thing. Has the last row changed at all? No, because the pivot column entry there was 0. So when the pivot column entry is 0, that row doesn't change at all. That's a nice thing. That saves some time actually. Anyway, so now we can write down these CBs. So what are the CBs now? Well, CB for X2 is 3. And now let's find delta J. Okay, so 3 into half is 3 by 2, minus 2 is minus 1 by 2. So is it optimal? No, so we need to do one further step. 3 into 3 is minus 3 is 0, so that's okay. Oh, next one is also not so nice. 3 into minus 1 by 2 is minus 3 by 2, minus 1 is minus 5 by 2, which is worse than minus 1. Then 3 into 1 by 2 is 3 by 2, minus 0. And of course, these two are 0, 0. And finally, 3 into 80 is 240. So the current Z value is 240. But can we improve that? No. Can we improve the Z value? Yes, because there are two negatives. The fact that we have negative delta J means we can improve the Z value. So which one should we take this time? Remember the most negative. Which one is most negative? Minus 5 by 2. Okay, and what are the positive values here? Only these two, not this. Okay, so when we're calculating theta now, when we calculate theta, we don't include this first one. Okay, so just put a cross here because it's not, we can take this one. We can take, so 210 divided by half. How much is 210 divided by half? It's 420. Dividing by half is the same as multiplying by 2. So theta here is 420. Uh-oh. Oh God. Is there space? Oh, there is space. And 180 divided by 2 is 90. So which one of these is less? Of course, 90. And so this is our new pivot here. Pivot entry is 2. Okay, so now we're going to go further down. Okay, so let's take something a little further down. Okay, so what are the new basic variables? X2 remains basic, S2 remains basic, S3 is replaced by X3. So we'll have X2, S2, and X3. Okay? Okay, so what do we have now? Now we have to divide pivot row here by 2. So what do we get now? Minus 1 by 2, 0, 2 by 2 is 1, 0, 0, and half. And 180 by 2 is 90. Okay? Yes? Agree? All right. Now, what happens next? My identity matrix. Where will my identity matrix come? Well, X2, that means the second column here, will become 1, 0, 0. Then S2. S2 is this one. 0, 1, 0. And then X3 will be 0, 0, 1. Okay, so first step is dividing the pivot row by the pivot entry. Second step is writing down the identity matrix. And identity matrix comes in this same order as the basic variables. Okay, next we have to fill all these empty spaces. So let's do that. So start at 2. So I'm doing this one first. 2 into half is 1 minus 1 into minus half. So minus half. So 1 minus half is half. Divided by 2 is 1 by 4. Right? Everyone has followed, no? Okay, I'll show it to you with arrows. This into this, that's 2 into that, minus this into this. So 1 minus half, which is half, divided by 2 is 1 by 4. Next one is this one. So this into this, minus this into this. So 5 by 2 and minus into 2 is 5 plus 1 by 2. 5 plus 1 by 2 is 11 by 2. Yes or no? 11 by 2 divided by 2 is 11 by 4. Right? Everyone agrees? Okay. Next one on this side. 2 into 1 by 2 minus half into 0. So that's 1 divided by 2 again is 1 by 2. So this doesn't change. Then 2 into 1 by 2 minus half into 0. Again, 2 into 1 by 2 is 1, divided by 2 is 1 by 2 again. So this column doesn't change also because of this 0 entry. All right, next one. 2 into 0 minus half into 1. So that's plus half, divided by 2 is 1 by 4. 2 into 0 minus 1 by 2 into 1. So minus 1 by 2 divided by 2 is minus 1 by 4. Okay. Last column. 2 into 80 is 160 plus half into 180. So 160 plus 90. 160 plus 90 is 250. Divided by 2 is 125. And last one, 2 into 210 is 420 minus half into 180, which is 90. So 420 minus 90 is 330. 330 divided by 2 is 165. Okay, so my new basic feasible solution is x1 equals 0, x2 equals 125, x3 equals 90, s1 equals 0, s2 equals 165, s3 equals 0. Okay. And now again I calculate delta J. So what is CB? Well, here it's 3 and here it's 1. Okay, so let's see what I get. So what is delta J? Oh, okay, this is a long one. 3 into 1 by 4 plus 1 into minus 1 by 2 minus 2. Oh, this is also going to be negative. So 3 into 1 by 4 is 3 by 4 minus 1 by 2. 3 by 4 minus 2 by 4 is 1 by 4. 1 by 4 minus 2, which is 8 by 4, is minus 7 by 4. Okay. So is it optimal? No, because there's a negative. These two automatically will be 0. Basic variables automatically have delta J equals 0. And this one also is automatically 0. What is this one? 3 into 1 by 2 will just give me 3 by 2. So that's positive. And here 3 into 1 by 4 plus 1 by 2 is 5 by 4. No. Yeah, 5 by 4. And Z, 3 into 125 is 375. 375 plus 90 is 465. Is it optimal? No. Why? Because negative. Okay, so in our next step, hopefully we'll get something optimal. So this is our entering variable. And now what do we do? Aha. Okay, so now we need to calculate. See, this is negative, so This time this will not be included. But what are the other thetas? 125 divided by 1 by 4. What is 125 divided by 1 by 4? 125 into 4, which is 500. Okay. Okay. And here 165 divided by 11 by 4. 165 divided by 11 is 15. 15 into 4 is 60. So which one is less? Really 60 is less. And so this time, this is going to be our pivot. Oh, it's not a very nice number, but anyhow. Okay, anyhow, we're just one step away, so nothing to worry about really. Okay, and here. Okay. All right, so what are the basic variables now? X2, X1, and X3. Okay, X2, X1, X3. So all variables become basic. Okay. All right. So what do? The pivot row we divide by the pivot entry. So this becomes 1, 0, 0. So 1 by 2 is the same as 2 by 4. 2 by 4 divided by 11 by 4 is 2 by 11. Okay, so this becomes 1. Oh. 1, 0, 0. Okay. Now, 1 by 2 divided by 11 by 4 is 2 by 11. 1 divided by 11 by 4 is 4 by 11. And minus 1 by 4 divided by 11 by 4 is minus 1 by 11. Okay. 165 divided by 11 by 4 is 60. Okay. And now we're going to cross multiply. So before that, where do I write my identity matrix? Well, first column goes here, second column goes here, and third column goes here. Oh, sorry. Okay, rest of the things I have to do by cross multiply. So 11 by 4 into 1 by 2. First one I'll do with arrows. So this minus this. So 11 by 8 minus 1 by 8 is 11 by 8 minus 1 by 8 is 10 by 8, which is 5 by 4. 5 by 4 divided by 11 by 4 is 5 by 11. Right. Next one is 0. Minus 1 by 4 divided by that is minus 1 by 11. Next is 11 by 16 plus 1 by 16. 11 by 16 plus 1 by 16 is 12 by 16, which is 3 by 4. 3 by 4 divided by 11 by 4 is 3 by 11. Okay. Last one is 11 by 4 into 125. So 11 by 125 divided by 4 minus 1 by 4 into 165. So 11 by 125 minus 165. How much is that? Okay. So, all right. We'll do it in Excel over on this side. 11 by, anyone happens to have a calculator? No? Okay. Doesn't matter. So 11 by, all right, what was it, by the way? I'll keep the denominator same, right? So 4 is the denominator. I'll leave 4 in the denominator. So I'm multiplying numerators. 11 into 125 minus 1 into 165. So 11 into 125 minus 1 into 165, right? 165, right? Yeah. Okay, how much is that? So that's 1210 divided by 4, right? I have to divide that by 11. So 1210 divided by 11 is 110. I'll get 110. Very, very simple. Yeah? Okay. Or same, okay, anyway, doesn't matter. All right, next one. Okay, so here 0 plus 1 by 2 into 1 by 2 is 1 by 4. 1 by 4 divided by 11 by 4 is 1 by 11. Next one is 0 plus 1 by 2. 1 by 2 is 2 by 4. 2 by 4 divided by that is 2 by 11. Last is 11 by 8 minus 1 by 8. So 10 by 8. Cancel the 2. So 5 by 4. 5 by 4 divided by 11 by 4 is 5 by 11. Last is 990 by 4 plus 125 by 2. 125 is by 2 is 250 by 4. So 990 by 4 minus 250 by 4. 990 minus 250 is, so 990 minus 250 is 740 by 4. No. It's not, no, sorry. 990 by 4 minus, okay, that is 160. Okay, let's do it through fractions actually. All right, so let's do this again. It's not 250, sorry. 990 by 4, okay, minus, or plus rather, minus becomes plus, right? Plus 2 into 165. 2 into 165 is how much? Okay, I'll write this 2 into 165. 2 into 165. Okay, so what do we get? 1320, again divided by 11. Divided by 11. This divided by 11 gives us 120. 120. Okay, so x1 equals 60, x2 is 110, x3 is 120. And let's find delta J now. So this is 3, this is 2 and 1. So what is delta J? Well, all of these are 0, 0, 0, 0. Okay, the interesting thing starts here. So 3 into 5 plus 2 into 2 plus 1. So 15 plus 4 plus 1, 15 plus 5 is 20 by 11, right? The first one is 20 by 11. Now next one, minus 3 plus 8 plus 2. 8 plus 2 is 10, 10 minus 3 is 7 by 11. And last one, 6 minus 2 plus 5. 11 minus 1 is 10 by 11. Okay, all of these, the important thing is, all of these are positive. And now what do I do? This 310 plus 120 plus 120. So 240 plus 310 is, 330 is 560, yeah? 5, 3 plus 4, 570. Okay, 570. 3 plus 2, 570. Okay. All right, now, last time did I show you how to solve this in Excel? No. Did I show you in Torah? I didn't show you in Excel, is it? I'm sure I showed you. Huh? Solver, no? Did I show solver or not? Then why are you saying no first? Every student will know, no, sir, you never taught us anything. I know that, but Try to remember something. I'm sure I did solve. Did I solve through Torah using that graph? Did I solve? I solved through that. Yeah, you're confusing me. Right. All right. Now, so in fact, I showed you how to get Torah also. We tried to get Torah through net or something. Do you remember? Okay. All right. Let me see if we can get Torah is here. So let me solve the same thing through Torah, and I'll show you the method that they use. Slightly different from what I taught just now. Slightly different. Okay. So linear programming. We did this, right? Yes or no? Yeah, of course we did. So LPP with 3 variables, 3 constraints is what we have, right? 3 variables, 3 constraints. So what was our thing? 2, 3, 1, right? Coefficients were 2, 3, and 1, right? 2, 3, and 1. Here this was, what was it? 1, 2, minus 1. Okay, where is it? 1, 2, minus 1. 1, 2, minus 1. I think this doesn't register as 2. 2, minus 1, 1, minus 1, 0, 2, right? And these are less than or equal to 160, 140, and 180, right? Yeah. Yes, good. Okay? All right, so let's solve it. Oh, so button is here. Okay, so let's solve it. Okay, no need to save the data. And of course, we can solve it graphically. Now, we can use, let me show you the way they do it. Okay, so they're going to use, and this is all Slack, right? Iterations using all Slack studying. So all of them are Slack. Okay, so let's see how they do it. Okay, so same things here. 1, 2, minus 1. This is the identity matrix. Okay, in the next iteration, okay, the pivot is 2. Is that what we have? Pivot was 2. Okay, and we can just compare. So if you're confused, you can just solve it through Torah and compare your solution with it. Okay, so now notice they're using slightly, no, they have the same thing, minus 2, minus 3, minus 1, and now minus half, 0, minus 5 by 2, 3 by 2, 0, 0, 240. Is that what we got? Yeah, minus 1 by 2, 0, minus 5 by 2, 3 by 2, 0, 0, 240, right? Okay, so next let's see what they do. So most negative is this one, and pivot I think is this one, right? Pivot was this 2, right? So we just click next iteration. Pivot is 2, so now it's minus 1.75, so minus 7 by 4, right? Minus 7 by 4. Minus 7 by 4, yes. So minus 7 by 4, 0, 0, 3 by 2, and 5 by 4 here. And 465. Is that what we got? 465. Okay. Again, this is going to be the entering variable. So next step. And its iteration 4 is up to. Okay. So now when we go to the last step, this is the optimal solution. So 0, 0, 0. Something anyhow, we have some fractions here, whatever the fractions are, 11, 20 by 11, whatever. Okay. So those will come here. Okay. Fine. And then you have, so our optimal solution is, oh God, whatever. Everything is divided by 11, so, fine. Or we can go back and get the final solution as follows. So solve, and the final solution will come. No, we don't want iteration. We'll just take final solution. The final solution is, so x1 equals 63.64, x2 equals 109.09, x3 equals 121.84, and z equals 576.36. If we simplify, if we write this in decimals, we'll get the same thing. Okay, so everyone is confident about doing this? Everyone is confident about doing this? I'll just put it on silently. Yes? Please practice it. It's a little, I know it's a little confusing. We'll also do one with greater than other types of constraints in one moment. Okay? Right? So, will you all practice this over this weekend? I don't think we have a class tomorrow. So probably next weekend we'll have 2 classes. So practice this, and if you have doubts, we can address them in the next. Okay, now, why, so far we've only dealt with less than or equal to constraints. Why do you think that's the case? Well, there's some big problems that happen when we don't have. Okay, let me show you what happens when we have greater than or equal to constraints. Actually, this is a nice diagram. Maybe, otherwise, shall we save it or what? It's recorded, huh? Okay, we'll just save it once. There's no harm in saving it. Someone may want to read it. So, simplex problem 1. Okay. No. I'll call it regular. No, we'll call it regular simplex method. Simplex problem. Okay. You'll see there's some other types of simplex that will happen. Okay. So everyone is ready? So let's talk about a simple problem like this. Okay. So let's have a problem like, suppose we're going to maximize again. Maximize, say, z equals, say, x1 plus 2x2. Okay, x1 plus 2x2. Subject to, all right, let's keep it simple. x1 plus x2 less than or equal to 100. Okay. And let's have something like 2x1 plus x2 greater than or equal to, say, 40. Okay. All right. Okay. So how do we put this in standard form? Well, if you remember, for less than or equal to constraint, we have to add a slack variable. For greater than or equal to constraint, we subtract surplus variable. Right? Now, there's also something, did I tell you about artificial variables also last time? Artificial variables? For the moment, let's pretend that we didn't know about artificial variables. I'm going to show you why we need artificial variables. Okay, so what we'll do is, we'll just, can I directly go to the table? I'll directly go to the table and show you this directly in the table, okay? So, but, okay, anyhow. Here's our table. Oh, sorry, I need vertical lines here. So, one vertical line this way. Okay, and one vertical line over here. Okay, all right, so what are the variables? Okay, x1, x2. All right, so slack, first one is slack, S1, second one is surplus, S2, and you'll see I've intentionally kept some space there, right? There's a reason, we'll see in a minute. So let's write down our constraints now. 1, 1, 1, 0. Oh, God, what is this? 1, 1, 1, 0, 100. Right? So added a slack variable there. For the second constraint, 2, 1, 0, minus S2, right? 2, 1, 0 minus S2, right? My zeros are becoming really horrible. Yes? So, first question. Do I have an identity matrix? Do I have an identity matrix? Oh, sorry, by the way, I have to write 40 here. So, do I have an identity matrix? No, because this is minus 1. So, can I write S1, S2 here? No, because if I write S2 here, this is saying that minus S2 equals 40. So, S2 will be minus 40. But can variables take negative values? No. So, this cannot be a basic variable. That's why I need an artificial variable. That's why I bring in an artificial variable in the second constraint. So it will be 2x1 plus x2 minus s2 plus a1. And now I have an identity matrix, s1, a1. And so now a1 can be a basic variable. Yes? Everyone can see? Yes or no? But what is this point? So, at this point, what is the value of x1? x1 is 0. What is the value of x2? x2 is also 0. So, at this point, x1 and x2 are both 0. But as you can see, x1 and x2 both equal to 0 will not satisfy this constraint. So, to start with, this basic feasible solution is not even feasible. And why is it not feasible? Because of this artificial variable. We've introduced this artificial variable to get this identity matrix, but in doing so, we are not at a feasible solution. So the first priority is to get it into the feasible point. And how do we do that? Make A1 equal to 0 as quickly as possible. So what we do is, we're going to do this problem in two phases. In the first phase, we're going to remove the artificial variables as quickly as possible. This is called phase 1. Okay? So, currently, as long as artificial variables are basic, so as long as we have artificial variables written in the basic column, we are in phase 1. Write this as phase 1. And the priority in phase 1 is to get rid of these artificial variables. So, ignore all other variables and take CB as CJ as minus 1 for artificial variables. Okay, you'll see that this will remove the artificial variable as quickly as possible. Okay, so let's see what happens. So what is CB now? So only variable with any value is A, so this will be minus 1. So what will delta J be? So 2 minus 1 into 2 is minus 2. Everything else is 0, right? Oh, 1 second. This is minus 2. Minus 1 into 1 is minus 1. This is 0. This is plus 1. This is minus 1 minus minus 1, so 0. And this we don't need really. So what will happen? So what is the most negative delta J? Minus 2. And so this is most negative delta J. What is the least value of theta? Here theta is 100 divided by 1. Here 40 divided by 2. Which one is less? Clearly 40 divided by 2. Huh? And so what is happening? The artificial variable is leaving. This is our purpose. The whole purpose of this step was to remove the, and that's what's happening. Removing the artificial variable from the basis. Now, the moment the artificial variable leaves the basis, we don't need it anymore. It's served its purpose. So now we are in phase 2. Okay, so now we are in phase 2. And now what are the basic variables? S1, X1. S1, X1. Okay? Okay? So now we can just forget this column. Not needed anymore. It served the purpose. We don't need the artificial variable anymore. The moment it leaves the basis, we are now going to be in a feasible point, at a feasible point. Okay? And now because of that, we have reached phase 2. Okay? So we'll write phase 2 here. This was phase 1. So we can just forget about all this actually. We can forget it existed even. Okay? And now we bring back our CJs. What are the CJs? This is just 1 and 2. Okay? So what is CB now? CB is 1. Oh, I'm sorry, I have to do the calculation. I'm sorry, I got carried away. All right? Let's do the rest of the calculation. The method is the same after this. Divide pivot row by pivot entry. So divide this row by 2. So we get 1, 1 by 2, 0, minus 1 by 2. This column, don't worry about it all. And 40 by 2 is 20. Okay. Now, where will the identity matrix come? In the S1, X1 columns. So 1, 0, 0, 1 will come here. This is 2 minus 1, so 1 by 2. This is 0, again plus 1 by 2. And this is 2 into 100 minus 1 into 40. So 200 minus 40 is 160 divided by 2 is 80. Okay? Very simple. And now let's get delta J. So 1 minus 1 is 0. This is 1 into half minus 2. Half minus 2 is minus 3 by 2. This is 0 and this is minus a half. And this is 20. Is it optimal? No. Right? Definitely not optimal. So, what is the entering variable? This is now our entering variable, and which is exiting. Both of these are equal. So, immediately this becomes exit. So, x1 entered, immediately it's being taken away for x2. So, actually, we should have entered x2. That would have saved us. Anyhow, you never know beforehand. Okay, so now it will be S1, X2. Never know beforehand which one is going to be. Divide by half, which is the same thing as multiply. You'll get back this thing. Actually, we could have saved a whole step here, but anyhow, how would we have known really? Okay, so this becomes 2, 1, 0, minus 1, and I'm just forgetting this, and 40. Just forget about A this month. So these are, so I've respaced it. Okay, now where is the identity matrix? Here and here. Right? S1, X2. And now we cross multiply. This is 0 minus a half. Minus half divided by half is minus 1. This one is 1 by 4 plus 1 by 4. So 1 by 2 divided by 1 by 2 is 1. This is 80 by 2 minus 20 by 2, which is 60 by 2 divided by that is 60. Okay? Very simple. And now CB is 2. Yeah? So what is delta J? Well, 2 into 2 is 4, minus 1 is 3. 2 into 1 is 2, minus 2 is 0. 2 into 0 is 0. That's nice. But 2 into minus 1 is minus 2. Is it optimal? No, I'm afraid one more step. And this is 80. I'm afraid there's one more step. Okay. So what is the most negative delta J? Minus 2 this time. And as we said, this has to be the pivot because the only positive entry here. Okay, so S1 now gives rise to S2 or gives way to S2 and X2. Okay, nothing to do. There's already a 1 here. So this row doesn't change at all. So minus 1, 0, 1, 1. I'm ignoring this is AS2. And this is 60. Okay, now what happens? X2 becomes 1, 0. S2 becomes 0, 1 here. Okay, 2 minus 1 is 1. 0 plus 1 is 1. 40 plus 60 is 100. And now, hopefully, this will be optimal. So CB is 2. So delta J is how much? 2 minus 1 is 1. 2 minus 2 is 0. This is 2. This is 0. And this is 200. Is it optimal? Yes. Okay, so the moral here basically is, okay, anyhow, okay, we can do one more of these, I suppose. But the moral here is, when we have greater than or equal to, or equal to, as a matter of fact, even for equal to constraints, we cannot just have slack variables. We have to introduce artificial variables. And an artificial variable is a troublesome thing. First thing is to remove artificial variables. That's why we do first phase, to remove the artificial variables. And after the artificial variables are removed, we're back in the feasible region and we carry on with the usual simplex method. I know it's a little difficult. Just practice it. You have about 1 week's time. Practice it for the next week. If you have difficulties, we'll again revise a little. But don't worry. I know sometimes you have very annoying fractions that come, especially if we're dealing with larger numbers. The fractions get worse and worse. But don't worry. If at all, it'll be simple type of thing, okay? But the whole point is, after this, we're going to move towards solving things using Excel and whatever, and doing case studies with them. So that's the more important thing. The applications are more important. We needed this method, as we're going to see. There's an important, these delta J's, even though, okay, they look innocuous, they're very, very important as they turn out. Those are where the sensitivity analysis is going to come from. Okay, so we're going to study what it means in a few. Let's see if we can do it today or maybe next time. Actually, next time is preferable. We'll do one more of these. Shall we do one more of these? Little more complicated one? Okay, so let's have one with less than or equal to and greater, and also one equal to. Let's see in the more general case of that. Okay, so everyone is ready? Oh, by the way, let's also, let me show this in Torah as well. Okay, so let's go to main menu, linear programming. This time, okay, let's just call it LPP, 2 variables, 2 constraints. The same problem, let's do again. Which chapter in the book? Okay, very good question. All right, really good question. Who is it? Rajesh, huh? All right. All right. Okay. Now, the textbook that I've given you perhaps does not have this, but this one has. Okay. And it's one of the chapters here. I think towards here. Oh, what happens? I think it's somewhere here. Oh, God. Either it comes as, in one of the appendices. Okay, let me just see. Oh, no. Okay. Then, oh God. No, this is not what I want. Oh, sorry, that's wrong. It's in one of these. Okay, 1 second. Or maybe it's in this version of the book. Is it the same one? Okay. Good question. It is. Okay, maybe this version of the book doesn't have it, huh? Okay. Let's search for it. How do we search here? Find. Simplex method. Where is it? 17 to 17, 17. Huh? What is 17 to? It says that it has it. Seventeen to, yeah, that's what. This is appendix. Okay, before appendix is 15, so 17 is not there. I see. All right, I'll find it. It's okay. It's the old version has it, so I'll find the older version. This is the 11th edition. I think the previous edition, 14th edition. I think 13th edition has it. I'll get it. No problem. I'll find it for you. Don't worry. Okay, but very good question. Okay. Anyway, so what we were going to do another problem. Okay. So everyone is ready. So I think I'll save this one also. It looks nice. Where did I save that one? Here, huh? Okay. This is this one, and we'll call this two-phase simplex problem. Okay. Okay. So now we can do this. Okay. So let's have. All right. Okay. So a simple one. Let's keep the numbers simple so that we don't struggle. So let's have. Oh, we were, yes, sorry, yes, Tora, of course. Yeah, I'm sorry. Yeah, we were solving in Tora, yeah. Thank you. Okay, so the previous problem itself, anyone remembers the objective function? 1, 2, 1, 2, yeah. 1, 2, and 1, 1, 2, 1, right? And this was less than equal to 100, and this is greater than equal to 40, right? And this is greater than, okay? Okay, so, all right, so, of course, let's first solve it graphically. So, our constraints are like this. And remember, in the beginning, the first tableau, we were at 0, 0, which you can see is not feasible. And so, what that artificial variable method does, it starts at a non-feasible point, brings it to a feasible point, then from here we went to here, and then lastly to here. Okay, so it moves. So anyhow, now when we solve this, in this case, because, all right, so because it has an artificial variable, if you see, there's a two-phase method. God, where did it go? Right, there's a two-phase method. There's another method called M method, but let's just do this with two-phase method, okay? So two-phase method, okay? So to start with, we have these, okay, in first iteration, all right? So phase 1, okay, it's taking, it's taking this, so the same thing that we got. It will take x1 first. Then in the next iteration, now these are the things here. Now we'll get phase 2, so we'll get -1. So this will come next. X2 will come in next. Okay. Okay, so this is the next one. And then in the next iteration, we'll get the optimal solution. So now Yeah. Oh, where is it? It's further down. Okay, so now x2 has come in next. Then s2 will come in next. Okay, and finally we get the same thing. And so x2 equals 100. They've called it sx3, whatever. So this is s1, s2. So s1 comes in. Okay, so all right. So we get the same things. The notation is slightly different, but method is one. Okay, so again, as you're practicing, if you get confused or something, you can always just check the step in Torah. The reason, so actually, the Torah was invented for this reason. It's for students to learn step by step each of these methods. That's why it's doing. Otherwise, who needs each of the steps? We just need the final solution. Actually, in applications, we just need the final solution. So this was done so that people could learn. Okay, so let's do one more problem. Okay, I think that'll get, okay, let's see. All right, let's have, say, 2x1 plus 3x2 and minus x1, 3x2 here, minus x3, okay, is our objective function. Let's have, say, x1 plus x2 plus x3. Let's start with a simple one. Let's say this is all less than equal to, say, 100. And suppose, say, x1 plus 2x2 is, okay, minus x3, let's take, is suppose greater than or equal to, what can it be greater than or equal to? Maybe it's greater than or equal to, okay, 60. That sounds nice. Okay, greater than or equal to 60. And finally, let's put x2 minus x3 should be equal to, let's say, 20. Okay. Just for a moment. Okay, x2 minus x3. So, okay, I think this should work. Or maybe this is a bit too high. Yeah. Okay, I'll just change this. It may be a little too high. So let's make it small, 10 or something. Yeah. Just make it 10. Otherwise, if it, yeah, y will just work. Okay, so let's try this one. So x1, of course, x1, x2, x3, non-negative. Okay? All right, so now how many variables will we have now? Well, we have variables x1, x2, x3. How many slack variables will we have? Well, one slack variable from here. From this constraint, we'll have one surplus variable and one artificial variable. And from this constraint, one artificial variable. So we'll have x1, x2, x3, s1, s2, a1, a2. So totally 7 variables. Okay, so we're going to use a bit of a longer table this time. Okay, a bit of a long table. Okay, and these are the potentially big table that we'll need. We may as well plan from the beginning. Okay, and is it straight or I don't know. Okay, that looks straight, huh? Okay. Okay, all right. So anyway, close enough. Okay, so what do we have as a variables? x1, x2, x3. Okay. x1, x2, x3. then S1, S2, and then A1, A2. Oh, there's plenty of space. Okay. Anyway, it doesn't matter. We'll slowly occupy the space. Or we can, okay, maybe I can spread it out a little more. Okay, so X1, X2, X3, especially for bigger fractions, we need more space to write them as well. Okay, there's still some space, but anyway, enough. Okay, so first thing is 1, 1, 1, 1, 0, 0, 0, and 100. Yes? Next one is 1, 2, minus 1, 0, minus 1, plus 1, 0. 10. Okay, so this constraint is minus S2 plus A1. Minus S2. And here, 0, 0, 1, minus 1, 0, 0, 0, and 1. Okay. And this is 20. Okay, so what are the basic variables? Basic variables are, of course, so slack variable will always be basic, so S1. Artificial variables will always be basic, so A1, A2. Okay, so the rule is, whenever we have this, slack variables and artificial variables will always be basic. So any constraint with a slack variable, automatically that will be the basic variable. Any constraint with artificial variables, automatically those will be basic. And again, to start with, this is phase 1, right? So minus 1 here, minus 1 here, minus 1 here, minus 1 here. So what is delta J? Okay, so let's see. Minus 1 plus 0 is minus 1. This is minus 2 minus 1 is minus 3. This is plus 1 plus 1 is plus 2. This is 0. This is plus 1. These are both 0. And doesn't matter what this is. Okay? So is it optimal? No. So this is our entering variable. And let's calculate theta. 100 by 1, 10 by 2, 20 by 1. Which one is least? 100 by 1, 10 by 2, 20 by 1. Least is 10 by 2, right? Okay, so this is the exiting variable, and this is our pivot. Okay, so now we'll have S1, X2, and A2. So, have we reached phase 2 yet? No, because artificial variables are still basic. Okay, so divide the pivot row here by 2. Oh, and first thing is, we can forget about A1. Don't need A1 anymore. Forget about that column. Okay, so now divide this by 2. So we get 1 by 2, 1, oh, too far to the left actually, minus 1 by 2, 0, minus 1 by 2, and 0, and 10 by 2 is 5. Okay? Alright, so now let's write down our identity matrix. So the S1 column is the first column of the identity matrix. X2 column is the second column. And A2 column is the third column. And now we can cross multiply. 2 minus 1 is 1 by 2. 0 minus 1 is minus 1 by 2. 2 plus 1 is 3 by 2. Minus 2 plus 1 is minus 1 by 2. 0 plus 1 by 2 here. And 0 again plus 1 by 2 here. 200 minus 10 is 190 by 2 is 95. And 40 minus 10 is 30 divided by 2 is 15. Okay, very simple. And let's get delta J. So this is minus 1. And so delta J is plus a half here. 0 plus a half here. 0. Thankfully, this is minus a half. And this is it. Okay, so thankfully, we'll get to phase 2, luckily. Okay, so entering variable is this. Now, this is negative. So just halves here, 95 and 15. Clearly, least one is 50. And so, this is our pivot. And so, luckily for us, both artificial variables have left the basis. Okay, so we're now in phase 2. Okay, so what are the basic variables now? S1, X2, and S2. S1, X2, and S2. Okay. So here we go. So divide throughout by 2 or by half, right? So we'll get minus 1, then 0, minus 1 here also, then 0, then plus 1, and 30. Yeah? And now I write down the identity matrix. Identity matrix is here. 1, 0, 0, 0, 1, 0 here, and then 0, 0, 1 here. Okay? And cross multiply. So 1 by 4 plus 1 by 4 is 1 by 2. 1 by 2 divided by 1 by 2 is 1. 1 by 4 minus 1 by 4 is 0. Then 3 by 4 plus 1 by 4 is 4 by 4. So 1. 1 divided by 1 by 2 is 2. Huh? Oh, okay, 2. Okay. Now, what do I get next? Minus 1 by 4 plus 1 by 4. So that's 0. Huh? Is it? Yeah, it is. Okay. And now, yes, on this side we have 95 by 2 minus 15 by 2. 95 minus 15 is 80. Yeah? And the last thing, 5 by 2 plus 15 by 2. That's 20 by 2. So 20. Okay, now what we do, we bring back Cj. So 2, 3, 1, minus 1, 2, 3, and minus 1 here. And now we have just a 3 here. So what is delta J? So 3 into 0 minus 2 is minus 2. 3 minus 3 is 0. This is 0. Minus 1 is plus 1. This is 0, this is 0, and this is 60. Is it optimal? No. So, what is the entering variable? Entering variable is this. And since this is negative and 0, this has to be us. And so we'll have x1, x2, and s2 as the basic variables. Oh God. Okay. And s2. Right? Okay. So yeah. Okay. So let's draw a line at the bottom. All right. So let's see. This is already a 1, so no change. 1, 0, 2, 1, 0. Forget about the space there. 80. So no change here. Now, identity matrix will come here. 1, 0, 0, 0, 1, 0, and 0, 0, 1 here. Okay, so 0 minus 0 is 0. Minus 1 plus 2 is 1. 0 minus 0 is 0 here. 0 plus 1 is 1 here. 20 minus 0 is 20 here. 30 plus 80 is 110 here. Okay, so what are delta j's? Well, this is 2 and this is 3. So delta j is 0, 0. Okay, this is 4 minus minus 1. 4 minus minus 1 is 5. This is 2. This is 0. And this is how much? 160 plus 60. 160 plus 60 is 220. And it's optimal. Okay. Very, very simple. So, as I said, it's not something you can wake up and suddenly do. You have to practice. Alright? So, practice this. I'll find the material and send it to you for the simplex method. Okay? I'll find some good material, send that for you. Okay. So, any other questions? Now, as we're going to see, these things that we've calculated here are related to, so the delta j's especially, are related to something called sensitivity analysis. And it's actually sensitivity analysis that we're going to use later in formulating or making further decisions related to the, the problem. So when there's a problem, when we're trying to apply this in practice in managerial decision making, it's a sensitivity analysis that will actually tell us how to go further and how to apply it. So we get an optimal solution, but how to modify the problem and how to see how robust the solution is, comes from the sensitivity analysis. So that will be our next topic after this. All right, so please practice this. Again, if you're having difficulties, don't worry. If it's very complex, if you have difficulties with fractions, don't worry. The type of problems that we're going to really do in this will not be that complicated. Nothing to worry about. But yes, the applications are far more important from this. All right, so any other doubts? Any comments, doubts, objections? No? Okay. All right. I know it's a bit, and in fact, actually, we can't devote much time to this also. That's the problem. In class, when we do it, we usually spend some 5-6 lectures doing this. Unfortunately, we just have one day for this, and that too just 2 hours. So I know the difficulties, but again, as you practice it, if you have difficulties, we can always do things offline. So don't worry. Okay? All right then. So we'll close for today. Oh God. Okay. So, all right. I think I'll take it because I'll stop recording.